Okay, that is going to conclude the intro or the recap of chapter 5. Okay, we're going to any other probability concepts that we need, we're going to see in chapter 6. Okay, so the intro to chapter 6. According to the Bureau of the Census, the latest family data pertaining to a family size for a small Midwestern town no more is shown in table 6.1. Okay, so we're looking at a table from your textbook. Table 6.1 has two columns: the size of a family, which looks like it can range from 2 people to 7 people, and the proportion, also expressed as a percent, because you see proportions in terms of decimals and then you see them in terms of percents, of families to the total number of families. Meaning that if we have this total population for the town of no more, if we look at this first row here, 0.4319 or 43.19% of those families had a size of 2 people. This table is called a probability distribution. It's a distribution of probabilities. The listing of all possible family sizes with the respective proportion of the families represents the probability distribution of family size. We can identify a probability by reading the table. Okay, so this kind of probability, reading from a table, is a little bit different from what we just discussed from Chapter 5. Chapter 5 is called classical probability, where you look at experiments and you look at, in theory, what should happen when you flip a coin or roll a die or spin a spinner. What we're looking at right here is an actual table of values. Somebody did a survey of people in this a census of people in this town and calculated exactly how many of the families had 2 people, 3 people, 4 people, 5 people, 6 and 7 people, and the percentage of the total for each of those family sizes. So when we ask, or when we are asked for a probability from the table, we can't conduct an experiment. It's just a matter of looking at the table and expressing the probability that's presented to us. So here's an example of a probability from the table. If a family from this town is selected at random, so you have all the families in the town and you randomly pick one of those families. What's the probability of selecting a 6-person family? So what's the chance that the family that you pick has 6 people in it? Well, if you look at the proportion of families in this town that have 6 people, which is 0.0283 or 2.83%, then the answer to this question, what's the probability of selecting a 6-person family, is just that, 2.83%. The chance of you selecting a family at random that has 6 people is 2.83%. Okay, so again, there's no tree diagrams when we answer questions like this. You have to be able to look at 2 types of questions and realize, well, in this particular question you need a tree diagram. But in this question, you would not need a tree diagram. It's just a matter of reading the table. Okay, let's look at random variables. To begin, let's consider a probability experiment like rolling a 6-sided die and taking note of the top-facing value. Okay, so we roll a die and we take note of the value that comes out on top. A random variable x is a variable x that can take on the values of possible random outcomes of an experiment. So if the experiment involves rolling the die, the possible values that we can have for x are the possible outcomes that we have for this experiment. Okay, so if x is a random variable that represents the top die value, then the random variable x can have 6 different values. 1, 2, 3, 4, 5, and 6. So the definition, a random variable is a variable x that can take on the values of possible random outcomes of an experiment. So the values of x in this particular experiment are 1, 2, 3, 4, 5, and 6. Okay, let's look at more examples. We can express this algebraically by just saying x equals 1, and then we put a comma next to each possible value of x. Consider a probability experiment of choosing 6 lottery balls from a pool of lottery balls labeled 1 through 99 and noting the number of single-digit balls selected. So you're choosing 6 and you're noting the number of single-digit balls. So a single-digit ball would be anything from 1 to 9. Okay, because a 10, which is right after 9, contains 2 digits, and that would not satisfy the experiment. So again, the definition of a random variable is a variable x that can take on the values of possible random outcomes of an experiment. X is a random variable representing the number of single-digit balls. So the random variable x can have 7 different values. 0, 1, 2, 3, 4, 5, and 6. So let me explain this again. The experiment was choosing 6 lottery balls. If you're interested in how many of those 6 are single digits, you can think of the values that could come out. Okay, if you pick 6 balls, it's possible that none of them, 0 of them, are single digits. It's possible that every one of those 6 balls is a double-digit number. But it's possible that you get one single-digit number. It's possible that you can get 2 single-digit numbers. It's possible that you get 3 or 4 or 5 or at most 6 single-digit numbers. Okay, it is possible that you can get all 6 balls having single-digit numbers on them when you pull them out of this pool of lottery balls. So the values for x, the possible values for x, are 0, 1, 2, 3, 4, 5, and 6. So we say x equals 0, 1, 2, 3, 4, 5, and 6. Okay, so it's the number of balls that have single digits on them when you're picking 6 lottery balls from a pool of balls labeled 1 to 99. Okay, let's try another one. Consider an example of rolling a die 3 times and counting the number of even outcomes. Okay, x is a random variable representing the number of even die values. The random variable x can have 4 different values, 0, 1, 2, and 3. Okay, so let's think about this. We roll the die 3 times. So you roll a die once, you roll a die twice, and you roll it 3 times. And each time that you roll it, you take note of the value that comes out on top. If you're considering how many even values come out on top, well, you could get 0 evens, you could get 1 even, you could get 2 even, or you could get 3 even. They could all be even. You're rolling the die 3 times, so none of them could be even, or all 3 of them could be even, or you could get 1 or 2 of them even. So the possible values of x are 0, 1, 2, and 3, where x represents the number of even die values. Okay, so x equals 0, 1, 2, and 3. We use the word random when we're discussing random variables because the values of x can assume, the values x can assume result from possible outcomes of a random experiment. Okay, so what we're talking about here are random experiments like rolling a die or choosing lottery balls. Those are random experiments, and the values that x can assume are possible outcomes of these random experiments. In the experiment of choosing a random family from no more, the size of the family is a random variable. Okay. So the size of the family, we're going to look at that column from the original chart for the census results. The random variable can have 6 different values because the size of a family ranged from 2 to 7. So 2, 3, 4, 5, 6, and 7. the values associated with a random variable have the probabilities associated with them. So we have the size of the family, which can take on the values 2 through 7. X can be any value from 2 through 7, and each value for X has an associated probability, the chance of it happening. So the probability that X equals 2 is 43.19%. The probability that X equals 3 is 22.76%, and so forth. The proportion or percentage which is associated with each family size is interpreted as the probability of each value for the random variable family size. So the probability of choosing a family of size 3 is equal to the percentage of families of size 3. So when we look at that table, we look and we see the column for 22.6. Okay. When we look at the table and we look at the family of size 3, the probability of us randomly choosing a family of size 3 is equal to 22.76% because that is the proportion of families of size 3. And what's the probability of choosing a family with more than 4 people? So we go back to the chart and we say, okay, 4 people has a probability of 21.04, but that's not what the question is asking. It's asking what's the probability of choosing a family with more than 4 people, which involves 5, 6, and 7. More than 4 means 5, 6, and 7. Okay, we don't include 4 when we say more than 4. So it's a matter of taking the percentages for 5, 6, and 7 and adding them up. So we would add up 8.68% plus 2.83% plus 1.15%, 1.51%. Okay, and that's going to be 13.02%. So we would add up those 3 percentages, and that would be the probability of choosing a family with more than 4 people. Okay, we're going to look at example 6.1 from your text. For each random experiment, define the random variable and identify the possible values of the variable. Okay, so we're going to try to figure out what does X represent and what are the possible values for X. If it's assumed that the largest number of children is 6 in a family, count the number of children within a family. So if we think about this example, you know that a family could have no children, so 0, and then we're told that at the most, the largest number is 6. So a family could have at the least 0 and at the most 6. So the number of children within a family means that X can take on the values from 0 to 6. So what X represents? The random experiment is the act of counting the number of children within a family. The value of X, or what X represents, the random variable, is the number of children. And the possible values of X are 0, 1, 2, 3, 4, 5, and 6. Okay, so the experiment is counting the number of children, the variable represents the number of children, and the possible values for the random variable are 0, 1, 2, 3, 4, 5, and 6. Okay, select a radial tire from the production line and determine the life of the tire, assuming no tire has ever lasted less than 20,000 miles or more than 85,000 miles. The experiment involves selecting a radial tire from the production line. Randomly selecting a tire from the production line is the experiment. The variable is the life of the tire. So the variable, what's different from tire to tire is the tire life. Now what are the values that X can take on? So X is the random variable, it's the life of the tire. What are the possible values for X? Well, we have to assume that no tire ever lasted less than 20,000 miles or more than 85,000 miles. So our possible values of X are any value from 20,000 to 85,000. Okay, so x can take on any value from 20,000 to 85,000 miles. C. Count the number of heads in 2 tosses of a fair coin. The random experiment involves tossing a fair coin twice, and the random variable is the number of heads. Okay, so how many heads do we have when we flip the coin twice? Well, we flip the coin twice, we can have no heads, and we can have 2 heads. So the possible values for the random variable range from 0 to 2. We have 0 heads, or 1 heads, or 2 heads. Okay, so having 0 heads would mean having 2 tails. Having 1 head would mean having 1 tail, 1 head. Having 2 heads would mean having 0 tails. Okay, let's look at the difference between discrete and continuous